Okay, thank you very much. Oh, wow, that's really big. Okay, good morning, everybody. So, as Thomas said, this is a joint project with Reinhard Werner. We are all from the Leibniz University in Hanover, and I apologize for this slightly mysterious title and the fact that the paper isn't online yet. In fact, we have been working very hard to get the papers online, and they should be appearing on this minute on the archive, because in Taiwan it updates at 9 o'clock. So you will find a short paper which gives you an overview and a long technical paper which gives you all the technical details in, well, any moment now on the archive. So let's get started. So as the title suggests, this talk is about embezzlement of entanglement. And for those of you who, like myself, are not native speakers, maybe you haven't heard the term embezzlement before. So let us maybe briefly take a look at what this actually means. So if you look at Cambridge Dictionary, it says that embezzlement is the crime of secretly taking money that is that is in your care or that belongs to an organization or business that you work for. And of course, instead of embezzling money, you can think of embezzling any kind of precious thing, whatever you have in mind, any resource. For example, you might have seen this nice little trick about chocolates. So you can think of slicing a chocolate in a very ingenious way like this and move around the pieces. And when you do that, you've taken out one piece, even though it seems like the rest of the chocolate returned to its initial state. So it seems like you've stolen a piece of chocolate without disturbing the remainder. Of course, that's not true. This is not really a good way to do embezzlement, because it's very easy to detect, right? You could just take this leftover bar of the chocolate and look how much it weighs, and you will find that one piece of chocolate has gone missing. So if you want to do successful embezzlement, you should do it in such a way that it's very hard to detect. And ideally then, it should be difficult to measure the amount of the resource in the first place that you want to steal. And this is something to just keep in the back of your mind maybe for the rest of the talk. Now, today, of course, we're not interested in embezzling money or chocolate or any of these worldly things. We are quantum information scientists, and we are interested in entanglement. So we want to embezzle entanglement. And of course, when we do that, what we have in mind is a bipartite scenario where we have Alice and Bob. So we have our big robot, very big here, Alice and Bob. And they have their local quantum systems, here represented by these laptops. And they somehow have access to a shared resource, which is represented by the safe on the slide. And the safe is in some quantum state omega. And now these agents can act locally, say, or maybe even classically communicate, and they want to embezzle entanglement from this resource. Now, let me go back to the definition of embezzlement. So one important word here is secretly. You don't want that everybody knows that you stole money from your company, right? So in our scenario, to make sure that no record of the crime exists, Alice and Bob should do it without classical communication, because otherwise there could be an eavesdropper that just intercepts their classical communication and publishes it somewhere or tells it to the police, whatever. So what we have in mind then is that we have Alice and Bob, and they can only do local operations without classical communication. And what they want to do is they want to take out of the safe an entangled state while not perturbing the state of the safe. Okay? So putting this into equations, what we ideally want is that we have some resource state omega, tensored with the product state, and we apply local unitaries, one for Alice, one for Bob. And what they get out is, again, the resource state and some entangled state psi. And they want to have the resource state not changing, because if it would change, you could potentially detect that they stole something from it. So this is the ideal scenario. Unfortunately, and this is impossible. Why is it impossible? Well, if you think about it, if they would do this, then they would create entanglement with local operations, which by the definition of entanglement should not be possible. And on a technical level, you can also just see this with a Schmidt decomposition. I should say that this is even impossible if you have non-separable infinite dimensional Hilbert spaces. This was argued in this paper. So this is really just impossible in this way. Okay. But as always, if you have a sort of no-go result, you should check whether it's stable under perturbations in some way. And indeed, 20 years ago, Van Dam and Hayden found this very beautiful family of quantum states of Schmidt rank n, which have these very peculiar Schmidt coefficients. And they showed that if you take these resource states and you want to embezzle a state of Schmidt rank d, then you can do so with an error log d over log n. So if you fix d and you increase n, this error becomes arbitrarily small. Or in other words, you can really embezzle while making the probability to detect it arbitrarily small. And such families of states are since then known as embezzling families of states, or sometimes universal embezzling families of states. You might wonder whether this error is optimal, and it basically is, due to Farnes-Oudenaarde continuity inequality. And second, it has been found that this scaling of the Schmidt coefficients as 1 over j is essentially completely generic. So under very general circumstances, if you want to have such a family, it will have show a similar asymptotic scaling of the Schmidt spectrum. Now, this scaling has an important consequence, namely, you cannot take the limit of these states. So even if you would embed these in an infinite dimensional Hilbert space, you cannot just send n to infinity and get a limit state, which of course should be true, because I just told you a slide before that you cannot do exact embezzlement in the way that I described it. Nevertheless, it's somehow an interesting question whether one could think of these omega n's as arising from one object, and sort of maybe these things could approximate one other object from which we can take the embezzlement. And this is some of the topic of today's talk. So today what we want to do is we want to ask 3 questions and answer them for you. So the first question is the following: is there a single quantum state that can embezzle states of arbitrary Schmidt rings to arbitrary precision? So instead of having a family of states, we have a single state, and we would call such a state an embezzling state. Second, are there systems where all states are embezzling states? This seems like a bit far-fetched, but okay, let's just ask this question. And third, if these exist, could they possibly exist in nature, like as actual physical systems and not just mere mathematical artifacts? And what we will try to do in this talk is to convince you that the answer to all of these questions is yes, they exist. And they might even exist in nature. Now, if you remember this no-go theorem that I told you about, you might think, okay, this clearly contradicts the no-go theorem. So what's the catch? Where's the trick that we have to employ? And the trick is that we have to go from a tensor product framework to a commuting operator framework. So you might have heard in the last years, in the context of Cyrilson's problems and WIP star equal RE, for example, that there's a difference between describing local parties by commuting operators or just as tensor products. And this is something that we find here in the context of embezzlement as well. I would also like to advertise this talk on Friday by Lauritz about the Schmidt rank for the commuting operator framework, if you want to know more about commuting operator frameworks and entanglement. Okay, so what is this commuting operator framework? Just to remind you, so usually if we describe quantum mechanics with local systems, what we do is we take one Hilbert space for each of the systems, we take the tensor product to obtain the global Hilbert space. Then the states are just vectors or density matrices on this Hilbert space. And the operators that Alice and Bob use to manipulate and measure their systems are the bounded operators on each of these Hilbert spaces. Now, in the commuting operator framework, we still have one global Hilbert space, but now it doesn't factorize into a tensor product. But nevertheless, the quantum states are just vectors in Hilbert space or density matrices on Hilbert space. But the operators of Alice and Bob are now just some sets of operators, subsets of the bounded operators, which are commuting. And in fact, what we usually assume, and this is a standard assumption somehow, is that these are not just any sets of operators, but these are algebras, and in fact, von Neumann algebras. So for Neumann algebra is one that is closed in the topology that's induced by taking expectation values with density matrices in your Hilbert space. You don't really have to know much about these for the rest of the talk. We will tell you what you need. In the tensor product framework, we have two properties that sort of automatically hold that we have to assume in the commuting operator framework. One is that what we will refer to as Hague duality. And it says that Alice can control precisely all of the operators that commute with Bob's operators and vice versa. And second, we assume that there are no classical degrees of freedom in our description. And that means that both for Alice's algebra and for Bob's algebra, all the operators that commute with the remaining operators of the algebra, all of them have to be proportional to the identity. Sort of, these are automatically true in the tensor product framework. So Hague duality just says then on technical terms that the algebra of Bob is the commutant of the algebra of Alice. Okay, and this no classical degrees assumption in technical terms means that the algebras of Alice and Bob are factors. This is just the technical word for what I said. Okay, so given this, we can now formally define what we mean by an embezzling state. So we have a bipartite system that is a triple of a Hilbert space, some factor, and its commutant. And an embezzling state is just a vector in the Hilbert space, such that for any finite dimensional entangled state, so this is just any, like a regular, finite dimensional quantum state, that's what everybody used to with working with. And for any such state and any error that you fix, there exist local unitaries UA, UB that map omega tensor some product state to omega tensor the entangled state that you want. So here the error really is in the unitaries. So if you want to reduce the error, you have to change the unitaries, but the state changes the same, stays the same. Okay, so this is an embezzling state. And now what we want to do, so if you remember in pure state entanglement theory, what we usually do is to go from entangled pure states to just the reduced states. And we can do so because Nielsen told us that entanglement theory on pure state basically reduces to majorization theory on the reduced states. And we would like to have something similar for embezzlement, and we will use something similar for embezzlement later on. And therefore, it's useful also to define monopartite version of embezzlement, or embezzling state. So a monopartite embezzling state is just a state on this algebra such that for every error that you fix in any state on n by n matrices, so this is just a density matrix basically, there exists a unitary that maps omega tensor a pure state to omega tensor psi up to error epsilon. And I should maybe say that these norms here, you should think of just trace norms. Second notion then that we need throughout the talk is that of a standard bipartite system, which is again something that we have in the usual tensor product framework if Alice and Bob have the same Hilbert space dimensions, namely that every marginal of Alice, say that means every state here on M, has a purification in our Hilbert space in this sense. So a state just assigns an expectation value to operators in the algebra, and this can be done with this vector in Hilbert space, and the same is also true for Bob, so for the commutant of our algebra. Okay, so these are the assumptions that we will take throughout the talk. Now, given this, what we can show is that as a first starting result, if you have such a standard bipartite system, then entanglement embezzlement is equivalent to monopartite embezzlement. So this is true on a qualitative and quantitative level. So if you can achieve embezzlement of entanglement with some error epsilon, you can do it monopartitely with epsilon prime and vice versa. So for the rest of the talk, what we can do is we can just focus on this monopartite version of embezzlement, which will make many things much easier. Okay, so this is similar to Nielsen's theorem in some sense. Okay, now if you have an operational task and you want to understand it, it's often useful to make it quantitative, to introduce a quantifier for the task that you have. So we also want to do that, and we want to quantify embezzlement, and this will be quite crucial for the remainder. So what we do is we introduce this quantifier of embezzlement. So I will walk you through the definition. So we take our state, which is supposed to be an embezzler or not. We want to measure its quality to act as an embezzler. And we check whether it can induce a state transition from some n-dimensional density matrix rho to sigma via just a unitary. Okay. So we minimize over the unitaries here. In other words, we basically calculate the distance of the unitary orbit of this state with this state. And then we maximize over all density matrices in all dimensions. Now, due to this maximization, you might think that this should just always be true, right? So intuitively, I mean, if you can somehow choose states here which always make this true, and this is a good intuition, and we will talk a lot about this in the rest of the talk, but still let us define this quantity as the quantifier of embezzlement. It's also useful to take some sort of optimized versions of this. So one is the best worst case error. So we find the best embezzler on our algebra M. And one is the worst one, so where we take the supremum over the states. And these quantities, kappa min and kappa min, are algebraic invariants of our von Neumann algebra that we started with. So these really only depend on the algebraic structure that we have here. And these will be very useful for the remainder of the talk. So this is really the central quantity for the whole talk that we talk about. Good. Now with this, we are already almost ready to state our main results. But I have to introduce one more math result to you, or a collection of math results. And this is the classification of factors, or von Neumann algebras. So remember, a factor is a von Neumann algebra where all the operators that commute with all other operators are proportional to the identity, and these can be classified into different types. So at first, we classify them into 3 different types called 1, 2, and 3. It's easy to remember. And then each of these has subtypes. For example, type 1 has subtypes 1n, where n is just a natural number or infinity, and these factors are just the bounded operators on the Hilbert space. So von Neumann algebras of type 1 is basically the setting that we're used to working in usual quantum mechanics. Then there are factors of type 2 and subtypes 2, 1, and 2, infinity. We will not say much about these for the remainder of this talk because they're not so important for us. And then there's type 3, which are labeled by continuous parameter lambda between 0 and 1. And these will turn out to be very important for us. So the first 2 types, 1 and 2, are also collectively referred to as semi-finite factors. And they are basically distinguished by the fact that they have a non-trivial trace functional. Whereas these type 3 factors, they're also called purely infinite, they don't have a trace. Where this means they don't have a trace means that if you take the trace, say, on the Hilbert space, then just always infinite for any element of the algebra. So they don't have a meaningful notion of a trace. Now with this, I'm ready to state our main result in an overview table, and it's the following. So we take the different types and subtypes of von Neumann algebras, and we look at kappa min and kappa max, which quantifies embezzlement. And you find that for type 1, you get that kappa min is 2, kappa max is 2, so there's no interesting embezzlement going on. For type 2, we have the same, kappa min is 2, kappa max is 2. So in these 2 cases, there are no embezzling states in our sense, even though there are embezzling families in type 1. Now if you turn to type 3, however, say here type 3 lambda between 0 and 1, then we find that kappa min is 0. And kappa min being 0 means that we can induce state transition between any finite dimensional states. So we have an embezzling state here. And in fact, if you look at type 3.1, we find that kappa max is also 0, so all states are embezzling. So these are the universal embezzlers that I mentioned in the beginning. Now for type 3 with lambda equal to 0, the story is very complicated. Sometimes there are embezzling states, sometimes they are not. So sometimes kappa min can be 0. We will say a little bit more about this in the end maybe, but there are some open questions there. Okay. So one thing I would also like to point out is that if you just focus on type 3, then within type 3, by looking at just at kappa max, these values of kappa max here, you can actually read off lambda from kappa max. That means that within type 3, embezzlement reveals Alain Connes' classification of type 3 factors. So we can really, in a quantitative manner, say that the type 3 subclassification corresponds to embezzlement, so to an operational task in quantum information theory. And with this, I would now like to hand over to Lauritz, who will tell you about how we actually get these results in a little bit more detail.
Yeah, thank you, Henrik. Yes, so I will go into how we get some of these results. For this, let me recall the slide that we had. So with this Nielsen type idea, we have to find a replacement of majorization theory. We want to study bipartite entanglement, embezzlement, and for this we want to understand the monopartite side, because that's easier. And on the monopartite side, we would like to use majorization theory, usually. But on von Neumann algebras, which are type 3, we don't have a trace. So we cannot use majorization theory. So we have to find a replacement. In the semi-finite case, we could use majorization theory. But from the table that Henrik just showed you, it is clear that we actually have only embezzling states in the type 3 case. So actually only embezzling states in the cases where we cannot use majorization theory. And the tool that we will use to replace majorization theory is called the flow of weights. The flow of weights was discovered by Alain Connes and Takazaki. It's a math result, which is very, very beautiful, actually. And we'll treat it here as a black box, like literally a black box. But the idea is that it takes in a von Neumann algebra, a factor in our case, and it spits out a classical dynamical system. So it somehow makes some problems classical. And this classical dynamical system captures a lot of the important information about the algebra. For instance, in the case where we're interested, where the von Neumann algebra is a factor, the classical dynamical system will be ergodic. And we can even read off the type 3, the Connes classification, from the flow of weights. The flow of weights is this classical dynamical system here. And we have that type 3 lambda factors, for instance, are precisely those where the flow of weights is a periodic classical system. And in addition to this flow of weights, due to Connes and Takazaki, we will use a refinement of it by Hagerup and Sturmer, which associate to a state on a factor a probability measure on this classical dynamical system, so a classical state. And we'll call this classical state the spectral state, because it captures the spectral information. And this will be our tool to get the results in the table. So maybe let me tell you a bit more about these. Sorry, forgot something. The thing that we're interested, of course, in is the embezzlement. So we're interested in is the state omega embezzling, and it will turn out that this corresponds to, under the flow of weights, corresponds to invariance. So we will see that the state omega is an embezzling state if and only if the spectral state is invariant. And that then lets us decide questions like, does there exist an embezzling state on this factor? How do I do that? Well, I look at its flow of weights. This is a classical dynamical system. And I have to study this classical dynamical system. Does it admit an invariant probability distribution? Sometimes it does, sometimes it doesn't. But that allows us to answer the question. And actually, we will even get a quantitative way of this correspondence. Yeah. Okay, now it works. Let me tell you a bit more about these spectral states. They were introduced by Hagerup and Sturmer. And they have this beautiful theorem which says that the distance of the spectral states, so this is the total variation distance of two probability measures, is precisely equal to the distance of unitary orbits of two states. And this is precisely what we need for embezzlement. You remember this embezzlement quantifier kappa, which looked at optimizing distance of unitary orbits. So we can replace that by optimizing the distance of spectral states. And we have to, for that, we have to look at the spectral states of product states. Okay. Something else that I want to say, yes, is this. What Hagerup and Sturmer also do is they explicitly calculate the range of this map. So we can say, given a probability measure on this classical dynamical system, is it the spectral state of something? And that will allow us to conclude if there exists an invariant probability measure on the flow of weights, then there is an embezzling state. So this is necessary for the one-to-one correspondence that I mentioned. Okay, so maybe to get some intuition, let's look at the flow of weights for a matrix algebra. That should be easy, right? The flow of weights in this case is just the positive real line, and the dynamics is given by dilation. That's ergodic. So what's the spectral state? The spectral state of a density operator, rho in spectral decomposition here, is given by the cumulative distribution function. So it's the probability density given by this formula. This takes in a number t and spits out the amount of dimensions that are taken up by eigenvalues larger than t. So why is that a probability density, you might ask? Well, let's see here the plot. If we want to calculate the green area, then we multiply m1 and p1, and we have this m2 times p2, and if we sum that up, we get 1. And this is, precisely what the cumulative distribution function does. And from this definition also, we see that this cumulative distribution function captures the full spectral information about the state. So we see here that the spectral state captures the spectral information. So maybe let's look at the time evolution of a probability measure here. So let's look at the cumulative distribution function of a state rho and let it evolve. We see that it gets flatter and flatter and flatter. And that means that there are no invariant probability distributions, because there cannot be embezzling states on a matrix algebra. We saw that. We had the no-go theorem that Henrik mentioned. And actually, we can use this to prove a bit more. Let's look at the cumulative distribution functions. And what I'm telling you here also works for spectral states in a way, because they're equivalent in this case. So let's look at tensor products. The cumulative distribution function of omega tensor pure state is just the distribution function of omega. But if I tensorize with a maximally mixed state, then I do get something different. I get a dilation of this function. So this stays probability density. And this is the flow of weights. This is the flow. The classical flow is dilations. So by tensoring with a maximally mixed state, I'm effectively implementing this flow. And this idea will be key to understand this one-to-one correspondence, which is very, very nice for us. So let's maybe look at the following result. If we have an embezzling state here, if we would have an embezzling state, then its cumulative distribution function would be 1 over t. So why is that the case? Well, we just apply this formula twice, this one. We know that for omega being embezzling, it follows that omega tensor a pure state is unitarily equivalent to omega tensor a maximally mixed state. And unitary equivalent states have the same spectrum, have the same cumulative distribution function. So we have this equality. But we have that for all integers. So applying it twice, we get this one, where we have a general rational number. This cumulative distribution function is by definition, it's right continuous. So I can take limits of this. I can take limits of rational numbers, and that's everything. So what does it become? Well, this formula. So we have 1 over t. But we cannot have 1 over t if this is a probability density. So we can conclude that there are no embezzling states solely on the basis of looking at these cumulative distribution functions. And actually, the same works for general semi-finite von Neumann algebras, not just matrix algebras. The reason is they have the same flow of weights. I can do the same argument. I can use the distribution function also in that case. And yeah, as I already said, this is a probability density, so it cannot be proportional to 1 over t. Also, this 1 over t should remind you of the 1 over j scaling of the Schmidt coefficients of an embezzling family. So that's an interesting connection, I think. Yes, so this is, again, to highlight this, tensoring with with a maximally mixed state or something else effectively implements the ergodic flow. So if we are now looking at general spectral states, looking at omega tensor psi and omega tensor phi, and I'm calculating the distance of their unitary orbits, what I have to do is I have to calculate the distance of the spectral states. But that means calculating the spectral state of omega at different time evolutions. And that then shows us that invariance of omega corresponds to being embezzling, corresponds to making these state transitions possible. So we can go back to this slide and add to it this nice theorem, which is a quantitative way of the correspondence. And actually, this is a miracle for me. It totally makes sense that the embezzlement quantifier is equivalent to this quantifier of invariance. So the invariance, the right-hand side quantifies how invariant is the spectral state of omega, but that they're actually equal, like precisely equal is yeah, I don't know, just nice for us, I suppose. But this is great. And with this, we can now prove the theorem that we had. So we can prove this table because we only have to calculate how invariant is a probability distribution under some classical flow. So we effectively made our problem classical. And yeah, now before we come to the table, again, let me tell you a bit about the flow of weights in type 3, because we have to look at that briefly. So in the type 3 lambda case, where lambda is non-extremal, so not 0 or 1, it's just a circle with rotation. And the radius of that circle is dependent on lambda, and it blows up at lambda equal to 0, and it goes to 0 at lambda is equal to 1. And actually, this picture is continuous in the sense that at lambda is equal to 1, the flow of weights is a single point. And on a single point, there's only one probability measure, there's only one flow, and this probability measure is clearly invariant. So for every state omega on a type 3 one factor, I get an invariant spectral state. So these are the universally embezzling systems. These are the systems where every state is embezzling. On the type 3 lambda case, we can also directly identify the spectral states of embezzling states. These are, of course, the invariant probability distribution. But what is an invariant probability distribution on a circle with rotations? Well, it's the uniform distribution. Something else that is the type 3 zero case. There, it's wide open. In the type 3 zero case, we can get every ergodic system. For example, we could get an irrational flow on a torus or something, and dependent on this system, there might be an invariant state or there might not be. But doing this analysis, we end up with this table that Henrik presented to you. And yes, with this, I would like to hand over to Alex, who is telling you more about the universally embezzling systems.
Well, thanks, Lauritz. And yeah, as Lauritz already mentioned, I want to tell you a bit more about universal embezzlement and why this actually characterizes these type 3 one factors. And by this also address this third question we had, namely whether these systems actually can appear in nature, at least in an idealized form. And first of all, we already learned that type 3 one factors are characterized by this trivial flow of weights. So the flow of weights is just this classical dynamical system, which consists in this case of one point. And of course there the dynamical system is trivial, everything is invariant, but you can also understand this in a bit more detail. And for this, these three properties are very important. So first of all, to understand the direction, why is a type 3 one factor universally embezzling, it's nice to know that there's this result by Kohn and Störmer, which tells you that these factors have an homogeneous state space, which means that actually all states lie in the same unitary orbit of this algebra. And moreover, these type 3 factors, I mean, Henrik already told you that these factors are so-called purely infinite algebras, and they are therefore in particular properly infinite, which means that they are isomorphic to themselves tensor product with an arbitrary B of H algebra for any H. So, for example, an infinite dimensional one, but also matrix one. So that means if you take a these tensor product states, which we are interested in embezzlement. So your embezzling state tensor, any state on a finite dimensional matrix algebra you want to embezzle from it, then you can identify this with a state on the algebra itself. And then this homogeneity of the state space actually tells you that you can map it to any other state with arbitrary precision. So this tells you that these algebras, only these two properties, should have this universal embezzling property. And on the other hand, if you want to go from universal embezzlement to type 3-1 factors, there's another way to understand it instead of using the flow of weights, namely by proving, and that's also what we did in the paper, that an embezzling state necessarily has maximum modular spectrum. So for those of you who don't know, I will give another intuition for this later on, but maybe for the experts, this is a nice statement. So you can prove that the spectrum of the modular operator of an embezzling state is always the whole real line. And since from this you can get the so-called S invariant of Conn, which should be also this for a type 3-1 factor, you can directly conclude that if an algebra where every state has this modular spectrum must be a type 3-1 factor. But now let me come to, well, this third question we ask, namely, well, do these type 3-1 factors actually occur in nature or in any familiar systems we know of? And first of all, I want to talk here about the case of infinite spin chains in statistical mechanics, because this gives you a very nice intuition in this context of why type 3-1 factors are actually universally embezzling. And then in the second part, I will talk about relativistic quantum fields and in which sense they also admit these type 3-1 factors and are therefore kind of a natural object where you should expect to be every state to be an embezzling state. Okay, so now for this intuition of the type 3-1 case. So in the following, I will assume that the algebra we are after is universally embezzling, and we want to check this type 3-1 property, and we will do this by appealing to this Conn-Störmer result, namely showing that any two states on these algebras are actually unitarily related, or at least up to arbitrarily small error. And for this, well, in a sense, you can take any infinite dimensional separable Hilbert space and just think of it as being provided by a spin chain. So for example, just take a spin chain and put a state on every tensor factor. So like this, pictorially. So you think of an one-sided infinite spin chain, and then you can actually observe in this case that this spin chain, or the Hilbert space you're getting here, that does not really depend on like finitely many of these factors. So to understand the structure of this Hilbert space and also the operators acting on it, you basically need to know the asymptotics of this sequence of states you're choosing here. So in other words, if you think of the Hilbert space and the algebra of operators associated to it, and you think of a state given here, then this object is essentially equivalent whenever you just take out a finite amount of states in the beginning of this chain. And this is a property we will exploit to obtain this type 3-1 property. So now, so in particular, if you look at the remainder, when you take out some of these some finite amount of factors, then you know, if you assume that your algebra is universally embezzling, then if the original state was universally embezzling, then also this remainder state must be universally embezzling. And this is related to this properly infiniteness, which I talked about, because this finite number of factors you take out here that actually corresponds to a finite dimensional matrix algebra. So this algebra here is essentially the original one tensor a matrix algebra, and by this properly infiniteness, we know that this is isomorphic to the original one. Okay, and now let us prove that it's actually type 3-1, and this is very pictorial. So what we want to do is, so we take this infinite spin chain, we take any two states on it, omega and sigma, and now we want to show that they are unitarily related. So what do? Well, we just take out a finite number of states here, then we know that these two are basically the same. But now, since we assumed that our algebra is universally embezzling, we know that these states here are embezzlers. Now we can just choose unitaries which map these arbitrarily close to one another. So this provides us an isomorphism here. So just closing the circle, we obtain that omega and sigma are actually unitarily related. So nothing easier than that in the spin chain case. But of course, I'm cheating a bit here. So, but if you make this precise, what this actually tells us, and this is a nice connection to this Van Dam-Hayden embezzling family, which Henrik also talked about in the beginning, is that we can show from this fact that actually any embezzling state on a hyperfinite algebra, and if you don't know what hyperfinite means, just think of it as a spin chain. So it means a bit more precisely that you have a dense increasing union of matrix algebras. So the idea would be in the spin chain case, you can basically get the algebra on the spin chain, but by just increasing the amount of factors you are taking into account. So these are so-called hyperfinite algebras, and if you have an embezzling state on that, you can just restrict this embezzling state to the first n copies of this spin chain picture. And then if you consider this as a family and the amount of factors you include, then that will actually turn out to be an embezzling family. And this, in a sense, gives you one of the directions. So we know that if we have an embezzling state, you get an embezzling family. But of course, you could wonder, is the converse true? And I will say something about that later on. So whether an embezzling family also gives you necessarily an embezzler. But let me now come to, well, answering this third question for you, namely, can these universal embezzlers also appear naturally? And for this, we want to, well, recap a bit about relativistic quantum field theory and especially its algebraic formulation. And the idea here is that instead of talking directly about quantum fields, what you want to do is you want to talk about observable quantities in a relativistic setting, which means that you want to talk about observations localized in space-time regions. And these space-time regions, here drawn as some subsets of this Penrose diagram of Minkowski space, basically are some open sets. Imagine them to be bounded or maybe even unbounded. And to each of those sets, you associate it for Neumann algebra. And it should have a net structure in the sense that when one of these regions is included in a larger one, then the operator algebras are also included into one another. And now we want to also include relativity in the sense of, well, causality or microcausality, how it's called. Namely, if you consider the causal complement of this region O here, which we denote by O prime. So this O prime should remind you of like the prime and the commutant of the von Neumann algebras. Namely, in that case, we demand that if this O is included in the causal complement of this region, then the actual von Neumann algebras will commute. So space-like separated measurements will commute in this setting. And we also want some kind of dynamical completeness of this theory in the sense that if you have this region O here and you take its causal completion, basically taking something like a Cauchy slice inside this region, and then every observable in this region should actually determine the observables in this causal closure, and this is denoted like this, where if you take the double complement, so you take the complement of O, you get this region, take the complement again, you get this O double prime, and this is like this relation now. So it's like dynamical completeness or the time slice axiom. And then, as Henrik also mentioned in the beginning, for some technical reasons, it's easier to assume that we also have something which is called Hag duality, which is actually related to this causal completeness, meaning that if you take all the observables in this region O, then everything that commutes with it should exactly correspond to the observables localized in this causal complement of it. So it's a kind of maximality condition if you split space-time. Okay, and now, well, assume we have now Alice and Bob, and they have some surface of common simultaneity, and so they split space-time, and you take the associated causal regions with the splitting, then what you have as a general result in algebraic quantum field theory is that these local algebras you associate with these regions are type 3-1 factors in that case. Yeah. And as Lauritz tried to convince you, well, this should imply that relativistic quantum fields are actually universal embezzlers, yeah? Because you cannot really avoid this type 3-1 conclusion in that case. And what I think is particularly nice about this, or we think, is that this gives a very nice operational interpretation of the diverging entanglement structure you have in the relativistic vacuum. Yeah? And in particular, I mean, there's some older results by Reinhardt and also Stephen Summers that tell you that you can violate Bell inequalities maximally in the vacuum state in relativistic quantum field theory. And this is now kind of a direct conclusion from the results we presented here, yeah? Because you have this embezzlement property for these local algebras, which tells you that you can basically embezzle arbitrary Bell pairs from the vacuum state in that case. So it gives a very nice intuitive explanation of this fact. Okay. And well, we can also quantify this again in terms of our embezzlement quantifier. Yeah? So if you look at this CHSH coefficient, which gives you kind of the maximal possible violation of Bell inequalities for one of these bipartite systems Hendrik introduced, then what we find is that this coefficient is actually bounded below by this expression in terms of the embezzlement quantifier. And well, this quantifier here was 0 when our state is embezzling, so meaning that if you have a universal embezzler, you actually get this maximal violation in that case. So that's also a direct conclusion from this result. And now one other question which we ignored so far is, which Hendrik mentioned in the beginning briefly, is can we also do exact embezzlement? Yeah, so can we put this epsilon to 0? We already know that in the tensor product framework this is not possible, but can we do it in the commuting operator framework? And here our results imply that actually exact embezzling states can only exist if your Hilbert space on which these algebras act is non-separable, which is, if you remember what I told you about the modular spectrum, a direct consequence of that, because exact embezzlement would mean that every value in the spectrum of an embezzling state has to be an eigenvalue, since the modular spectrum of an embezzling state was the whole real line. You have uncountably many eigenvalues, so you need separable Hilbert space. But if you want to really make this precise, well, you have to use some additional techniques like ultrapowers. Well, now let me basically conclude the talk by reminding you that we had these 3 questions. So we wanted to know, are there actually systems where you can have embezzling states? Second, are there systems where you have the fact that all states are embezzling, which we called universal embezzlers, and do these universal embezzlers actually exist in nature, which we also tried to convince you should be the case in quantum field theory. And then we had this nice relation of embezzlement with the Kohn classification of type 3 factors, with this slightly open case, or maybe also largely open case of the type 0 case. Yeah? So we know at the moment that within the type 3 case we can distinguish the different subtypes by embezzling, but if we could clarify also this case, which I will comment on in a second, then we could even distinguish using embezzlement the semi-finite case from the type 3 case. And well, I also tried to convince you that in the setting of spin chains or hyperfinite von Neumann algebras, it's actually relatively easy to understand why universal embezzlement corresponds to this type 3 property. And using this, that you can actually find these universal embezzlers in nature by using this kind of bipartite setting in quantum field theory. And with this, I will come to some open problems which you might want to think about. So the first one would be, and that's something I ignored so far, so in the setting of Alice and Bob, maybe let me jump back once more. Here we had Minkowski space split into these 2 regions, yeah? And if we do this, then of course these regions are unbounded, okay? And the question would be, well, can we actually localize these operations? And then also, can we explicitly determine them in a QFT? What is the relation with limits of embezzling families? Here we have a kind of no-go result for the converse, yeah, at least in a certain case, namely this Van Damme-Hayden family does not converge. And well, the question that was open for the type 3.0 case, can we achieve kappa min equal to 2 in that case or not? And with that, well, let me give you this as the last slide. And thank you for your attention, and hopefully by now you can also access our papers on this topic. Okay.
Yeah, thanks a lot. Do we have questions? Okay.
Thanks for the talk. I was wondering concerning these universal embezzlers in Minkowski space that you talked about. Do you have some intuition, or could you talk about how we could imagine they look or work? Are they just spin chains, or is it something different?
Well, actually, in this quantum field theory setting, you can just take the vacuum. You know? So the idea is essentially that, well, this entanglement structure of the vacuum fluctuations gives you this universal embezzlement structure. You know? So you can somehow steal embezzlement from, entanglement from the vacuum.
There was another question. Wait, there was a question there. Yeah, go ahead, and then I'll take yours.
Thank you. I think this is a naive question, but I just want to make sure I understand. I don't believe from what you say it's possible to embezzle one of these embezzling states. Can you tell me, is that true, and why doesn't it become possible?
Well, actually, that in certain settings that is possible, yeah, because you can take spin chains. For example, well, maybe I can go back to that slide. Let me see if it works. So, if you think about the spin chain picture here, yeah, so this spin chain, the type you get here depends on this family of state rho here. Yeah. So what you can do here is you can take a universal embezzler, which is a particular choice of this rho, so which gives you the type 3.1 factor. But then you can also take a family of states that gives you the type 3 lambda factor. You build a tensor product out of them, and then you could take the embezzling state on the 3 lambda factor, which also exists, and embezzle that from the type 3.1 factor, because the tensor product of type 3.1 and type 3 lambda is again the same type 3.1 you started from. So actually that is possible in that case.
Can I maybe add to that? Just a small comment. One thing we didn't show is that we also have a sort of super additivity property here, like in I don't know, capacities or so on. Namely, you can have the fact that you have two states which are non-embezzlers, and you tensor them, and now they are an embezzler.
Okay, yeah, please.
Just want to clarify. So you have this statement that if you want zero error, then the Hilbert space is non-separable. But you also have this table where it says when you have type 3.1, both K-min and K-max are 0. I feel like in that case, doesn't that mean the error is 0? Not really.
No, you still have approximation. So you can make the state, the error arbitrarily small as you want, because we take the inf.
That's the infimum.
Yeah, exactly. That's the infimum.
Okay. Also, just on this slide, you have this Araki-Woods construction of the hyperfinite type 3 factor. I'm just wondering, can you give me some intuition, because I understand that the lambda, this subscript enters in the state, right? So, but why the embezzlement sort of depends on this rho? Can you give some intuitions of why in the end the result depends on that? Or is just out of your proof?
Well, I'm not completely sure if I understand the question, but well, the idea is that I mean, first of all, the algebra you get here depends only on the asymptotics of the state. But what determines the type is essentially the possible ratios you can get in the eigenvalue spectrum of these rows. So in a sense, they need to be very mixing, if you want, to get these type 3-1 case. And the type 3 lambda is a kind of interpolation to get to this maximally mixed thing. But I mean, don't confuse maximally mixed with the trace. If you take the trace for these states, you get type 2. But it's kind of mixing of the modular operator in that case.
Thanks.
Okay, so we'll have one last quick question.
So this might be very naive. So I just want to understand the role infinity here. Mm-hmm. So suppose you have a finite size quantum computer and a finite size civilization. You want to use this. Like, is it actually doable?
Well, I think in that case you would have to restrict to this kind of family you can induce. So the idea would be then, I mean, I think for a single quantum computer it doesn't make sense. It would be necessary that you kind of consider like increasing the simulation size or the available bits you have, and then you could track this phenomenon of embezzlement to some degree. Does this answer your question, or no? Okay.
Maybe something I can add to that. You basically need to have infinite entanglement already to embezzle something from it. That you, like on the quantum computer, you cannot have that in an accessible way. In the vacuum, you do have infinite entanglement, but it's kind of hard to access that.
Maybe one thing here, again, coming back to this embezzling family. So, if you would construct like the vacuum of a quantum field theory by, let's say, a lattice approximation, for example, then this would tell you basically that to access this infinite entanglement in the limit of this lattice regularization, you need to operate on smaller and smaller scales of the system, because you basically have to refine your lattice. And this, in this sense, as long as you're restricting the resolution you have, you only get, I mean, your error will have an upper and a lower bound that you can achieve essentially. Okay.
All right, thanks. So let's thank all three speakers again.